Our next presentation is the role of meteorology in regulatory air quality modeling, presented by Kamal Gurur of the California Air Resources Board.
Hello everyone, my name is Kamal Gurur. I work in California Air Resources Board, and then I will talk about the role of meteorology in regulatory air quality modeling. This presentation was made possible by my colleagues, namely Jeremy Avis, who is our branch chief, Chansha Kai, who is my manager, and my other colleagues, Dazang Ying, Sarka Kulkarni, James Chen, Jin Lu, Zhen Zhao, and Daniel Chow. We have air quality concerns in California because of the complex topography, as well as the meteorological conditions that are present throughout the year. And emissions from human activities, such as on-road motor vehicles, consumer products, combined with natural sources, such as emissions from plants, wildfires, and volcanic activity, are either directly emitted or react in the atmosphere to form pollutants, such as ozone and particulate matter. Meteorological conditions, such as cold temperatures in winter and high temperatures in summer, combined with low winds and shallow planetary boundary layer depth, can create stagnant atmospheric fluid conditions that are favorable to build-up of pollutant concentrations near the ground. Health concerns of air quality are several. Number one is particulate matter, with a diameter less than 2.5 micrometers, can enter deep into the lungs and decrease lung function, irritate airways, create difficulty in breathing, and even result in premature death in vulnerable populations, such as people with heart and lung diseases. Similarly, elevated ozone levels can cause coughing and sore throat, and even damage the lungs with prolonged exposure to high ozone concentrations. Many research studies indicate that presence of PM2.5 and ozone in the air, either individually or together, increases the risk of premature death. In our regulatory modeling approach, there are four main components: meteorological model, which affects emissions, pollution formation, and transport; emissions from both human activities, anthropogenic, and natural, biogenic sources; and then the boundary conditions that we give the air quality model, which present background pollution concentrations, such as transport from other surrounding areas. Air quality model, which predicts ozone and PM concentrations. How are these models are used at California Air Resources Board? We demonstrate that quantified emission controls or reductions will lead to attainment of the national ambient air quality standards, for example for PM2.5 and ozone. We estimate the effectiveness of specific control strategies, such as retrofitting diesel trucks with PM traps to reduce PM emissions. We also predict the transport and dispersion of toxic pollutants and to assess the health risk. Why are meteorology measurements important? Meteorology affects emission rates. Meteorology measurements constrain our meteorological modeling. Meteorology measurements are necessary to evaluate our models, such as, does the model represent observed conditions? Meteorology also affects the formation of pollutants such as ozone and PM. Meteorology affects the transport and dispersion of pollutants as a whole. Certain emission categories are strongly affected by meteorology. For example, biogenic sources, which are natural emissions from plants, and residential wood combustion. Activity is increased on cool days. Plants emit volatile organic carbon, or simply or shortly VOC, which contributes to ozone formation and to secondary PM2.5 formation in the atmosphere. These emissions are strongly dependent on both temperature and sunlight. For example, almost no emissions at night and in the cold winter months. As a result, it is critical to have those measurements, particularly temperature, to accurately estimate biogenic emissions. Seasonal variability in biogenic emissions are important. This figure shows monthly average biogenic VOC, or reactive organic gas emissions, for the San Joaquin Valley Air Basin in 2012. When you look at the figure, you can see that emissions peak in the summer with higher temperatures and drop to near zero in the winter. Peak summertime emissions can be many times the VOC emissions from human activities, so biogenic sources play a critical role in atmospheric chemistry. Residential wood combustion activity, for example wood stove or fireplace burning, is strongly influenced by temperature. This figure shows daily RWC activity in San Joaquin Valley in 2013, where activity is determined as a function of temperature. If the weather is cold, there will be more burning. Meteorological conditions have a first-order impact on the ability of an air quality model to reproduce observed conditions, since the atmosphere is the driving force for all constituents in the air through diffusion, dispersion, and transport. The atmosphere creates many meteorological conditions that can be favorable or unfavorable for the formation of elevated concentration of air pollutants. Thus, we first need to understand the atmosphere in a region with air quality concerns, using meteorological models as a tool before we attempt to understand air quality in that region. The meteorological models are initialized using the gridded meteorological data that is generated by other approved models, such as North American Regional Reanalysis, or shortly NAR, in which all observed meteorological data collected over North America at many service and operator stations is distributed to model grid box using the dynamical and thermodynamical principles of the atmosphere. This figure shows an example of NAR reanalysis data that we use to initialize our meteorological models. The figure on the left is for temperature, and the figure on the right is for wind vectors near the surface. When we look at the temperature, warm colors or higher temperatures are represented by red, and then colder air temperatures are represented by blue colors. Similarly, higher wind speeds are represented by red, and then calmer winds are represented blue to the white on the right near the surface. Meteorological model results are routinely evaluated against observed meteorological data to assess model performance. While the choice of available model options can generate different model results, meteorological modelers typically choose model options that give the best model performance using personal experience from many modeling applications carried out using different model physics. If model performance is not within acceptable EPA criteria, then iterative process of testing different model physics options and inputs is carried out, including options for nudging of the observed meteorological data over the gridded initialization fields using analysis, service and/or upper air grid nudging, and observational nudging options. Essentially, we are trying to force or nudge the model towards the observations. There are several meteorological models that are available to use in regulatory modeling, while we use Weather Research and Forecast, or short WRF or WRF model approved by the EPA. Choosing the best meteorology can be quite challenging. For example, in this figure on the left, we are showing a piece of the grid cell that we use in the model, and there are two stations that are close to each other, and the terrain is flat. If you look at the observed data collected at station 5723 and 2114, they look quite different. Those two figures shows the wind, speed, and direction. If you look at, for example, the first figure for 5723, the dominant wind is from the northwest. Actually, it's north-northwest. But if you look at the figure underneath for station 2114, it is from the north-northwest, west, and south. There's even an easterly component. So as a result, observations are not consistent. Then the question is, which is correct and which one we can use it? As a result, we conclude from this that wind is not further represented in the model, and then as a result, we have to choose which station data we can collect or we can use in the model. In this figure, there are two stations somewhere else, but the observed conditions for the wind speed and direction are quite similar, and then terrain is flat. As a result, observations are consistent with each other, and then winds well represented in the model. Summertime ozone in San Joaquin Valley is a big concern for us. But before we talk about more, let's look at the complex part of California. If you look at the figure, you will see that along the coast we have coastal mountains, and towards Nevada, on the eastern part of the California, we have high Sierras, and in between sandwiched San Joaquin Valley as well as northern Sacramento Valley. Associated with stagnant high-pressure systems, coupled with elevated temperatures, trap air masses within the valley that result in a buildup of ozone over multiple days. Within the next few slides, we will be showing summertime case studies in San Joaquin Valley with two examples. This figure shows how the meteorology impacts air quality modeling on ozone. We are showing the results of two numerical model results. Blue with the first model run, red is the second model run, and then black is the observations. When we look at the wind speed, temperature, and relative humidity comparisons, we see that wind speeds are lower and better represented with the second model run. However, peak temperatures too low in the second model run, but better represented in the first model run. When we look at the relative humidity is higher and better represented with meteorological model second run. When we give two model runs as an input to air quality model, we see that peak ozone is better represented with second model run, because second model run had lower wind speeds associated with less mixing and higher ozone concentrations, while first model run had higher temperatures associated with enhanced ozone chemistry and higher ozone concentrations. Second model run had a higher relative humidity that can be associated with lower ozone. Also, second model run had lower mixing heights, which we have not shown here, which is associated with less mixing and higher ozone concentration. This is not always intuitive, which meteorology will result in better model performance for ozone. Now let's look at the impact of meteorology in air quality modeling for particularly PM formation. In wintertime, PM formation in San Joaquin Valley is a big concern for us. Cold and stagnant conditions lead to formation of and buildup of PM2.5, primarily directly emitted PM2.5 from residential wood burning, charbroiling in restaurants, and ammonium nitrate formation in the atmosphere from emissions from NOx from motor vehicles and ammonia from farming operations. Wintertime case study in San Joaquin Valley also we conducted, where we will be showing two simulations that we carried out for 2013. In previous slides, we had shown the comparisons for two meteorological runs on ozone formation. This time we will be looking at the comparison of two model runs on PM2.5 formation. The figures on the left column is from the model run, first model run, and then the columns on the right is from the second model run, in which we are improving the relative humidity by making changes in soil moisture. We are also improving the near the surface air temperature and near the surface wind speed and wind direction. The figures in this slide show the impact of first meteorological model run on PM2.5 formation at Modesto, Visalia, Fresno, and Bakersfield stations. When we look at the comparisons, we can see that total PM2.5 formation is reasonably simulated by the first model run in Modesto, which is located in the northern portion of the San Joaquin Valley, but is underpredicted further south in Visalia, Fresno, and Bakersfield. Similar to the previous slide, this slide shows the impact of the second meteorological model run on the formation of PM2.5 at these four stations. When we compare the results, improved PM2.5 simulations due to enhanced nitrate formation, which is driven by improved relative humidity estimates and better representation of the southerly transport of wind speed within the San Joaquin Valley. As part of our regulatory air quality modeling approach, we also carry out dispersion modeling. Dispersion modeling is used in CARB's risk modeling to track the transport, dispersion, and deposition of toxic emissions from individual sources, for example, diesel PM, metals, and toxic VOCs. Emission sources can be treated as point sources, for example, from glass manufacturing, area sources, for example, from lawn and garden equipment, or line sources, for example, from motor vehicles or trains. Dispersion modeling uses a combination of observed and modeled meteorology. The accuracy of the meteorological parameters, particularly the wind field, is critical to dispersion modeling. In our regulatory air quality modeling for ozone and PM, our modeling domain is typically the entire state of California, although we can still focus on smaller domains with higher spatial resolutions. For dispersion modeling of toxic chemicals, we typically focus on smaller domains. This figure shows toxic risk model of diesel PM that are coming from many sources for South Coast. Figures on the left shows emissions from on-road area with a 1 kilometer area-wide coverage and point sources. Figure in the middle shows diesel PM coming from on-road emissions specifically, and figure on the right shows the associated cancer risk, which could be coming from several categories: diesel PM, metals, or toxic VOCs. When we are carrying out dispersion modeling, again, the meteorology is very important. If the meteorology is inaccurate, then everything is wrong. In summary, meteorological measurements play a critical role in CARB's regulatory modeling program. From the modeling of natural emissions from plants to regulatory air quality modeling and air toxics risk assessments, meteorology is one of the most important considerations. As emissions continue to be reduced, it becomes even more important to accurately model the meteorological conditions that lead to elevated pollutant levels, and meteorological measurements are a key piece of that work. In the past, emissions were high enough that errors in the meteorological fields were less important, but that is no longer true. We are highly supportive of any and all surface and upper air meteorological measurements in California.
All right. Thank you, Kamal, for that presentation.
Yeah, thank you.
We can go ahead and take questions now if anyone has those. I see one. What is the grid size that you run on the WRF model over the California domain? Do you run higher resolution nested runs over regions of high pollution, such as a wildfire?
We typically run our WRF model with 3 nested grids, and the outer grid typically is 36, and the second one is 12, and then the inner grid is 4. However, we have been experimenting with an even higher resolutions, inner grid with being the 3 kilometers. And then we also get other modeling support from other universities and research institutions around the country with 2 kilometers. Bottom line is this: whether there's a wildfire or not, we carry out the same spatial resolution throughout the California domain. So but if we have a specific study, we might focus on a smaller domain when even within higher resolution. And these are for our large long-term studies. But we also, if we are looking at a dispersion modeling, then the resolution is in the order of hundreds of meters instead of kilometers. I'm not sure if this answered the question, but that's my answer.
Thank you, Kamal. Any other questions? Hansa says thank you.
Thank you. I don't see these questions or answers here, although I'm looking at it. But anyway.
One moment.
Sure. No, I see it. Interesting. That's fine. Yeah.
We've got, what is the performance of the model in ozone?
As I was trying to give an as clear as possible a definition of how the meteorological model performs in air quality modeling, and then unfortunately it varies. In certain time of the year, we get a better model performance. In certain time, we don't get it. So we do an iterative approach for specifically answering in ozone. Ozone is typically a summertime problem. And then so for summertime, we might get a really good model performance in 1 year. We may not be able to get it in other years. So it varies. However, within using an iterative process, we try to improve the model performance by using different model physics option, or even putting a different initial conditions. There are other questions. Let me try to answer them.
Yeah. So for PM 2.5 and ozone, what observed data, hourly or daily or monthly averages, do you used when comparing to the modeling outputs?
We have quite a few of air quality monitoring stations throughout California, and then the exact number varies depending on the operating conditions. So we use the hourly data and some of them, and then daily data. And then we use those data to compare against the output that we get from a regulatory air quality modeling. And then for regulatory air quality, we typically use TMAC. So we compare them to these hourly observations to model outputs. And then, yeah, go ahead.
Sorry. So do you find the current meteorological measurements from air quality agencies adequate for air quality modeling needs?
It's a good question, and thank you. First of all, we appreciate all the support that we get from our air quality and our other agencies throughout California. The more is the better, because there's no limit, or there's no upper limit for getting the air quality or any observational data, whether it's meteorological data or air quality data. For that, we appreciate all the input and then the support that we get. Currently, and then we cannot say that the data that we get is sufficient or not sufficient. However, there are this has nothing to do with wherever do we get the data or who gives us the data. And there are other areas that we do not have enough data collection sites, and there are some other areas that we get enough or dense enough network that can give us a good comparison.
When building your models, are you using different equations for different seasons, or is it just one master equation for your model?
For meteorological modeling specifically, which is my field, and then this is also true for air quality to a certain extent. For meteorological modeling, obviously, the equations do not change, although the way that we use equations can change. The equations that we use are Navier-Stokes equations that are built into the models. But by using different nudging or weighting, we can manipulate how those equations respond to what we are trying to get. And then so we can completely eliminate or increase the efficiency of these equations. So the equations do not change, but the way that we use can change depending on how good the model performance we get.
Great. Well, we are running out of time. There's one more question.
Sure.
Do you have information on the most commonly used MET equipment? I wonder if there's a MET system that performs better to produce better quality data.
I will try to understand this question. Is that first of all, there are certain instruments that are used to measure wind speed, wind direction, temperature, pressure, and then humidity. And humidity is not typically directly measured, but they're using dew point temperatures. We get an idea of what the humidity is, and then mixing ratio is not directly observed. So every year, different meteorological, various meteorological instruments are come up, and then they improve the efficiency of obtaining a good quality of meteorological data. So there is no one particular set that we adopt, and then whatever that we get, we use them all. And then obviously, we look at the data quality, and then so all the input that we get from the data provider is important for us.
Thank you. So that's all the time we have for questions. If you have any more, please feel free to email Kamal. Sorry we didn't get to these last couple questions. We'll see you all in the next session.
All right.
Thanks.
Thank you for
Thanks,
all
Kamal.
participating. Oh, thank you.